Welcome to the deep dive, where we take a massive stack of sources and distill it down into the core knowledge you need. Today, we are strapping in for a pretty high-speed tour of the Snowflake SQL API. And this isn't just a generic read-through of the docs. Our sources really zero in on the gritty details of integrating this API into modern web environments, specifically looking at frameworks like Laravel 10.
Yeah, and this is such a critical layer for developers. I mean, if you're building services that sit on top of massive data infrastructure, this is your entry point. The SQL API is, at its core, a RESTful API. You use it to access and update data in a Snowflake instance.
So it's not just for select statements.
Oh, not at all. It gives you programmatic control over almost everything. Query operation, sure, but also creating tables. That's your DDL, your data definition language. And of course, modifying data, which is DML, is an incredibly powerful interface.
Okay, so our mission for you today is pretty clear. We want you to walk away with a really solid grasp of the foundational principles here. We're going to explore why a developer might actively choose this over, say, a traditional database driver. And, most importantly, we have to unpack the architectural and security nuances, those things that directly impact your application's design.
Right, with a big focus on efficiency and just robust protection.
So let's start with the why. Why does Snowflake even need this API?
Well, it really comes down to their whole value proposition. They became a leader in what you could call data as a service by letting companies just shed the overhead of managing infrastructure. You offload that entire management burden, and then you can focus your resources on what really matters, data warehousing, analysis, and all the big AI and ML initiatives.
And the numbers are just staggering. I was looking in the sources. Snowflake claims a 612% increase in customer ROI. I mean, that's a tectonic shift in value.
It's huge. And they're handling the volume to back it up. We're talking over 2.6 billion queries per day across their platform. This thing is built for massive scale.
And just for context, remind us of the core architecture. How does the API fit in?
So Snowflake is cloud-native, multi-clustered. You have the storage tier with all the compressed data, the compute tier with the virtual warehouses doing the work, and then you have the service tier. Think of the service tier as the brain. It manages metadata, authentication, and the crucial step of routing queries. The API talks directly to that brain.
Okay, so my instinct as a developer is always, why reinvent the wheel? A traditional database driver. That should be easier, right? Why would I choose to build an application using a REST API instead of a familiar driver?
That is the perfect question, and it really speaks to the limitations of those drivers. I mean, as of when our source material was published, Snowflake only supports about 7 of them. Things like Go, Python, PHP, PDO. If you're working outside that ecosystem, you're stuck right away.
But even if you are in one of those, there's still a catch.
A big one. Every single time a driver gets an upgrade, that means you have to do intensive testing. And it could mean disruptive code changes in your application. That's a huge maintenance risk.
So the API is a lighter weight, lower maintenance alternative. It's language agnostic.
Precisely. And it really, really shines in specific architectural scenarios. Say you're building a multi-tenant application. One of the sources mentioned a real-world example, Black Diamond 360, or maybe a native mobile app. Or you're just in an environment where installing drivers is restricted or complicated. The API just removes that whole local dependency headache.
And there's another thing here, an operational advantage that drivers just can't match. Something about the status page.
Yes, this is a powerful little nugget.
Oh.
Because it's an HTTP interface, your application can actually programmatically query the Snowflake API status page itself.
Okay, that's a level of control you just don't normally get.
It's crucial for enterprise apps. It means you can tell instantly if an outage is happening at the Snowflake service level. So instead of your app just failing with some generic connection error, you can catch that status, handle the outage gracefully, maybe fail over to a cached result, and give a meaningful message to your user. It's a massive stability win.
That kind of control. It must mean the API itself is architected for this kind of independence. Let's unpack that. How does it actually work?
It's mostly RESTful, as we said. Everything communicates securely over TLS, and all the results come back in a JSON v2 format. And the API, at least at version 6.3, is highly focused. It's really just one resource with 3 specific endpoints for execution.
Okay, lay them out for us. What are those 3 endpoints?
First, you submit the job. That's an HTTP POSE to a PIV2 statements. You send your SQL there. Second, you check the status of that job. That's an HTTP GET request to a PIV2 statements, followed by a UUID ID.
And that UUID is the ID you get back from the first call.
Exactly. And third, you can cancel a running job, which is just adding cancel to the end of that status URL.
All right, let's focus on that second endpoint, the polling. If my app is constantly hitting that URL to check for results, aren't we just trading one kind of latency for another? What's the cost there?
Yeah, that's the question everyone asks when they're new to this model. But think about it. With a traditional driver, your application process literally halts. It has to wait for the entire result set to come back.
Yeah.
It's standing in line. The API gives you a ticket and tells you to come back later. When you submit the request, you instantly get a 202 accepted status code, along with that statement handle and the status URL.
Ah, so the key isn't that the query runs faster. It's that my application doesn't have to wait for the result.
Precisely. This asynchronous design fundamentally removes concurrency limits at your application level. Your app is free to go do other things, handle other requests, and this is exactly what enables those smooth, lazy loading interfaces we all want. Using AJAX or something similar to check back in later, keeping the UI snappy while a massive query runs in the background.
And while we're polling, what's happening on Snowflake's end? What are the states?
The processor is in one of three logical states. It's either in a sleeping state, just waiting check again, an error state, which returns an HTTP error code, or the one you want, a success state, which returns an HTTP success code and your JSON payload.
Okay, but Snowflake handles petabytes of data. How does the API get a truly massive result set back to my app without just overwhelming the connection?
Right, that's handled by beta partitioning. Large result sets get broken up automatically into these sequential chunks, or pages. Your first successful response only contains the first partition. If you need more data, you make subsequent requests to fetch the additional partitions. You can do it one by one or even in parallel if your app is complex enough to handle that.
All right, let's shift to optimization. This API is incredibly powerful DDL and DML access, so security has to be the absolute top priority. What are the non-negotiables here?
The sources are very, very clear on this. Because the API is so powerful, you must not use a user with high-level access like account admin or gadmin.
Yeah.
Never. You have to implement role-based access control, or RBAC, and custom tailor the API rules permissions based strictly on the principle of least privilege. Only grant the absolute bare minimum permissions the application needs to function.
And since we're authenticating with a key pair, we can't use multi-factor authentication, MFA, like a human user would. How do we make up for that security layer?
This is a critical point that people often miss. MFA protects a human. An API key protects a service account. It's a technical identity. So since you can't use MFA, you have to use an infrastructural substitute. The non-negotiable step here is to create a network policy that is tied to the specific server IP addresses your application runs on. And you assign that policy to the API user.
So even if the key pair was somehow compromised, an attacker couldn't use it unless they were literally coming from one of my server IPs.
Exactly. It locks down the source IP. It provides a crucial mandatory layer of security on top of the key authentication. If the key is stolen, the network policy makes it useless outside your infrastructure.
Okay, let's talk performance. SQL itself. I know this next point is going to make some developers wince, but we have to talk about selectRy. Why is this lazy practice so damaging with this specific API?
It creates two massive problems, and they're intertwined. It goes way beyond just pulling back extra data and wasting compute time.
Yeah.
The first problem is the structure of the JSON v2 result set. It's an array of data arrays, the results. They don't have column names with every single row. They only have the values in order.
So wait, so where are the column names?
They're defined only once, up in the result set metadata at the very top of the JSON payload. So to find the value for, say, the address column, your application code has to loop through that metadata to figure out which position, which index the address column is at.
Oh, that sounds incredibly fragile if someone adds a column to the table.
Your application breaks instantly because the ordinal position of the data you wanted just shifted. Your code is now coupled to the database schema in the most fragile way possible.
So the solution is just control, being disciplined.
Absolutely. Define your columns explicitly. Select created on, address, zippy. When you do that, you optimize the query by only pulling what you need, and you get total control over the ordinal position of each column in the data array. That makes parsing the results faster, cleaner, and way more predictable.
We also have to talk about security with user inputs, dynamic SQL. That brings us to bind variables.
Bind variables are completely essential. They're how you get clean, dynamic code and prevent SQL injection at the same time. It's all about separating the SQL statement from the values. You use a play as a placeholder in your SQL, and then you pass the actual values separately. The API processes them independently, so malicious input can't be executed as code. It's just cleaner and safer.
And for really complex logic like batch processing or data scrubbing, our sources say the best strategy isn't to code messy loops in our app, but to use Snowflake's own power.
That is the key. Don't repeat yourself. Or DRY principle right there. For those complex, repetitive jobs, you should leverage stored procedures and user-defined functions, UDFs, directly within Snowflake. You make one simple call to that procedure via the API, and Snowflake handles all the complexity. It minimizes network traffic and keeps your app code lean. It is worth noting, though, that the SQL API doesn't currently support calling stored procedures that use Python, so that's a limitation developers need to be aware of.
Wow. Okay, this has been an incredibly detailed breakdown. So to recap the main takeaways for you, the API offers this critical async flexibility over drivers. The core process is those three endpoints: submit, check, cancel, and polling for results. Security absolutely hinges on network policies locking down the source IP, and efficiency is all about avoiding select and using bind variables.
And if we connect all this to the bigger picture, you can see where this is going. Snowflake is heavily focused on integrating AI and ML capabilities directly into the platform. They're trying to democratize it. And what that means is that the foundational skill of being able to query, structure, and secure that data using a tool like the SQL API becomes more critical than ever for any developer building what comes next.
Right, the platform is evolving, giving you these powerful new tools right at the data layer. So the final question for you to consider is this. If the SQL API grants you near limitless potential and your primary defense is the principle of least privilege, how does your organization's governance strategy make sure that least privilege applies not just to simple select permissions, but to the powerful new AI and ML models you are about to expose through that very same API?